All right. A dilation is a transformation and the notation, whoops, would be capital D with a lowercase k, that produces an image that is the same shape as the original, but is a different size. A dilation stretches or shrinks the original figure. Okay. The description, let's see, do we want to put that? Yeah, the description of a dilation includes the scale factor, or ratio, and the center of the dilation. Usually the origin. The center of dilation is a fixed point. About which all points are expanded or contracted. It is the only point that does not change under dilation. Let's see. A dilation of scale factor K, whose center of dilation is the origin, is written like this. D of k for x comma y goes to let's say equals instead kx comma ky. Let's say on the back, let's put a couple more things. If the scale factor k is greater than 1, the image is an enlargement. Or in other words, a stretch. If the scale factor is between 0 and 1, the image is a reduction. Which you can also think of as a shrink. Let's see. It is possible but not usual that the scale factor is 1 comma, which would create congruent figures. So let's see, what do we want to put? Dilations create similar figures. Okay, that's good for that card. Let's go to 140. Properties preserved. Also called invariant under a dilation. Angle measures remain the same. Parallelism. Parallel lines remain parallel. Collinearity. Points stay on the same lines. midpoint. Midpoints remain the same in each figure. Orientation. Lettering order remains the same. So those are the things that remain the same. Now for number 6, distance is not preserved. So it's not an isometry. Lengths of segments are not the same in all cases. Except a scale factor of 1. Alright, let's do an example of one of these. Okay. Let's see. I think we're going to do this on a new card. We'll call it 141. Draw the dilation. Image of triangle ABC with the center of dilation at the origin and a scale factor of 2. Okay, let's do it. So let's say our original figure here is negative 2, 2. Um, 0, 2. And 1, negative 1. Okay, so let's say this is C, B, and A. Alright, just going to write down my notation for dilations. So it says it's a scale factor of 2, right? So my K is 2. So I'm doing a dilation of 2 on all of my x comma y points, which is going to be 2x comma 2y. I just multiply by my scale factor. So I have A, B, and C, which have points negative 2, negative 2, 1, negative 1, and 0, 2. So then I'm going to have an A prime, B prime, C prime of negative 4, negative 4, 2, negative 2, and 0, 4. So 1, 2, 3, 4, 1, 2, 3, 4. 2, negative 2, 0, 4. So this would be A prime, B prime, and C prime. Okay? So let's put a little comment over here. Notice how every coordinate of the original triangle has been multiplied by the scale factor . Okay, so that's good for example 1. Now let's do one more example. That was card 141, so we're on 142. Draw the dilation image of a pentagon A, B, C, D, E with the center of dilation at the origin and a scale factor of 1/3. Okay? Let's set this up on the back. Okay, so the original starts here at 0, 0. Actually, let me see if I want to write this. Yeah, let's do it like this. Our dilation is 1/3, which takes every x comma y point and makes it go to 1/3 x comma 1/3 y. So we have A, B, C, D, and E. A is at 0, 0. B is at 3, 3. C is at 6, 3. D is at 6, -3. And E is at 3, -3. So first let's plot those points. I got 3, 3. 6, 3. 6, -3. 3, -3. Okay. So we have A, B, C, D, E. Okay? Now, if we perform this translation on each one of those points, we would get A prime, B prime, C prime, D prime, and E prime. A prime is still going to be 0, 0, because anything times 0 is 0. B prime is going to be 1, 1, because 3 times 1/3 is 1, and 3 times 1/3 is 1. C prime is going to be, well, 6 times 1/3 is 2, and 3 times 1/3 is 1. D prime, 6 times 1/3 is 2, and negative 3 times 1/3 is negative 1. And E prime, we're going to have 1 and negative 1. So A prime is also at 0, 0. B prime is at 1, comma 1. C prime is at 2, 1. D prime is at 2, negative 1. And E prime is at 1, negative 1. So here is our shrunken pentagon. That's it. Okay? So let's put a little statement here also. Notice how every coordinate of the original pentagon has been multiplied by the scale factor. One-third. Okay. So that is it for dilations. Let's look at card 143 now. Okay. A rotation is a transformation that turns a figure about a fixed point called the center of rotation. Rays drawn from the center of rotation to okay. Rays drawn from the center of rotation to a point and its image. Form an angle called the angle of rotation. An object and its rotation are the same shape and size, but the figures may be turned in different directions. Let's see. Okay. Okay. Unless told otherwise, the center of rotation is the origin. A positive angle of rotation turns the figure counterclockwise Okay. Give me 1 second. Okay. So let's draw a picture of this. Let's say we have a figure let's say this is A, B, C. Alright. And we're going to rotate it. I drew that not that good. We're going to have to erase that. Let me think actually for a second. Actually, I'm going to put something different on the back of this. Let's split this into 3. So if I divide 4 by 3, I get 1 1/3. So figure right there, right there. There's 3 rules that we really need to know. Oh, actually, we only need to know 2 this year. So I'm just going to divide this sheet in half. Okay, so first is a rotation of 90 degrees. All right, so an R of 90 degrees takes x comma y and makes it negative y comma x. So for example, if I had 3 comma negative 4 would go to 4 comma 3. Then you need to know a rotation of 180 degrees. So an R of 180 degrees takes x comma y and makes it negative x comma negative y. So as an example, if we take that same point 3 comma negative 4, we would get negative 3 comma 4. Okay? Now we have one more card about rotations. So this is 144. So I'm going to sharpen this. Okay. Properties preserved. Or invariant under a rotation. First, distance. So the lengths of segments are the same. Two, angle measures. Remain the same. 3, parallelism. Parallel lines remain parallel. 4, collinearity. Points stay on the same lines. 5, midpoint. Midpoints remain the same in each figure. 6, orientation. Lettering order remains the same. Okay. So let's go on the back and just draw a picture of a rotation. All right. Let's say this is the center of rotation. So now whatever this length is, about 2 inches to A. So I would go this would now be A prime. So I'm turning each one 90 degrees. So B is, let's see how far away B is. It's 1 inch. No, it's 1 1/8 inches. So this is B prime. So what I'm doing is I'm rotating each point 90 degrees, right? Because this is an example of a 90 degree, what I'm doing is an example of a 90 degree rotation by hand. It's a little easier when you have coordinates. So C is 2 1/4. So that's C prime. So here's my okay. This is an example of a 90 degree rotation. Okay. So from A to A prime, and from B to B prime, and from C to C prime. Each point has been rotated 90 degrees. Alright, now let's do, we should do one example problem. This would be card 145. You just sharpen this. Alright, let's see. Okay. Graph triangle ABC under a 90-degree rotation. Okay? And you're given the coordinates A is 2, 3, B 2, -1, and C -1, -1. Alright, so let's do this. Okay. Y, X, okay. So let's first plot our original. We have, well, let's actually write down our little statement, what we want to do here. So what we're doing is a rotation of 90 degrees, which is going to take x comma y and make it -y comma x. So they gave me original points A, B, and C. 2, 3, 2, -1, and -1, -1. So I'm going to rotate each one of those to get my A prime, B prime, and C prime, which will be -3, 2, 1, 2, and 1, -1. Okay, so let's do this. 2, 3. Two, -1. And -1, -1. So this is A, This is B, this is C. Now let's do the image. Negative 3 comma 2. 1, 2. And 1, negative 1. Okay, so there it is. A prime is this one. B prime is this one. And C prime is that one. Okay? And that's it for rotations. Okay, let's see. Alright, let's just take 1 minute and go back to okay. So I'm going on the back of card 133. This is for a line reflection, and I want you to write in big letters opposite isometry, and then the translation. So on the bottom of 138, let's write in big letters direct isometry, and then for dilation it is not an isometry, and then for rotation it is a direct isometry. Alright, this is card 146, and we're finishing up our transformations stuff. We're going to talk about compositions of transformations. So when two or more transformations are combined to form a new transformation, the result is called a composition. The result is called a composition of transformations. Don't know why. Okay. In a composition, the first transformation produces an image upon which the second transformation is then performed. Alright, so the notation reflection in the x-axis, and then this open circle means composition, and then a translation of 3 comma negative 4 is read as a reflection in the x-axis, no wait, is read as let's see, a translation of x plus 3 comma y plus 4 and then a reflection in the x-axis. Let's see. So where we had this R x-axis open circle T 3 comma negative 4, this part we do first, and this part you do second. Alright, and this little thing is the symbol for composition. Okay? So now on the back, let's put down, it is possible that a composition of 2 transformations may be renamed by one transformation. For example, the composition of a line reflection in the y-axis followed by a line reflection in the x-axis could be described as a single transformation of a rotation of 180 degrees about the origin. Let's see an example of that. So So let's say this is the X and this is the Y. Whoop. All right. So say we had some shape, like a triangle, right? And first we reflected it in the y-axis, and then in the x-axis. So you can go this way and then this way, or you can just go straight that way, which would be a rotation of 180 degrees. So a reflection in the x-axis that follows a reflection in the y-axis is equal to a rotation of 180 degrees. So that's an example of how you can replace a composition of transformations with one transformation. Okay? So this would be a rotation of 180 degrees. This could be our reflection in the x-axis, and this is our reflection in the y-axis. Alright? So that's card 146. Let's see. We're on 147 now. When a translation which remember is a slide or glide, and a reflection are performed one after the other, a transformation called a glide reflection is produced. You can glide first, then reflect, or reflect first, then glide. Since translations and reflections are isometries, a glide reflection is also an isometry. Okay, so on the back, let's draw a picture of what a glide reflection could look like. Say you have an object, like a triangle, and some line of reflection. First you could reflect it. So mine goes off the page a little bit, but that's not a big deal. You get the point. So first it goes reflection, and then what happens is we glide. Okay, so there's an example. So first you reflect and then you glide. Okay, we got one more. Let's see if we're going to write anything else on the front of this. No. Now we're on card 148. Okay, properties preserved. Also known as invariant. Under a glide reflection. So first we have distance. Lengths of segments are the same. Number 2, angle measures. Remain the same. Parallelism. Parallel lines remain parallel. Number 4, collinearity. Points stay on the same lines. Number 5, midpoint. Midpoints remain the same in each figure. Okay. So those are the things that are preserved or do not change or invariant. Now 6, orientation is not preserved. Lettering order does not remain the same. We actually don't need to put it there. So, a glide reflection is what we call an, let me just see how we labeled these other ones. It is an opposite isometry. Okay? And on the back, I think what we're going to do is an example. Let me pull one up. All right. Let's do an example of a glide reflection on a graph. Okay. Y and X. Okay. So let's say you have a triangle that goes from 5, 5 to 1, 3 and 2, 1. So this is your original triangle. A, B, C. A, and this was at 5, 5. B, 1, 3, and C, 2, 1. So, let's say first we do a reflection in the x-axis. Okay. So we have A prime, which is 5, negative 5. We have C prime, which is 2, negative 1. And B prime, which is 1, negative 3. So first we reflect it in the x-axis, and then we're going to translate it 5 units to the left. So let's see. 1, 2, 3, 4, 5. So C is going to go here, C double prime. There's B double prime. And A double prime will be right on our axis here. So A double prime is now at 0, negative 5. We'll just draw in our shape real quick. B double prime is at 1, 2, 3, negative 4, negative 3, and C double prime is at negative 3, negative 1. Okay? So this was the second thing you did starts first, right? So the second thing that happened was a translation of 5 units to the left, so negative 5, and 0 units up or down. Okay? And that was followed after a reflection in the x-axis. Okay? So let's see how we can work this out. First we had a translation of negative 5 comma 0, which takes all my x comma y's and turns them into x minus, oh, that was second, right? Already messing yours up. The reflection goes first. So a reflection in the x-axis takes all points x comma y and turns them into x comma negative y. So I had an A, a B, and a C. A was 5, 5, B was 1, 3, and C was 2, 1. And so what happened was I got A prime, B prime, and C prime, 5, negative 5, 1, negative 3, and then 2, negative 1, right? Then I did a translation of negative 5 comma 0, which takes all x comma y's and makes it x minus 5, y minus 0. So this time I started with my A prime, B prime, C primes, which was 5, negative 5, 1, negative 3, 2, negative 1, and they became the double primes. So 5 minus 5 was 0, and negative 5 minus 0 was negative 5. 1 minus 5 was negative 4, and negative 3 minus 0 is negative 3. And 2 minus 5 was negative 3, and negative 1 minus 0 is negative 1. Okay? So that's an example of a Glard reflection, which is a composition. It's one of the types of compositions. Okay? And let me see. If I rotate that thing, no, that'd be different. Let me just double check something. Alright, so that is the end of our work on transformations.